So welcome everyone to the virtual seminar in economic theory. Today we are very happy to have Meg Meyer from Oxford University, who will present the paper, A Welfare Analysis of a Steady State Model of Observational Learning. It's a joint paper with Eszter Kabos. The guest panelists are going to be, this occasion, Nageeb and Peter Norman Sorensen. The format is the format, as I said, is a 60-minute presentation followed by 15 minutes of questions. During the talk, please, we suggest that you post your comments, and although we're going to try to voice their comments if there are substantial or clarifications to make, we're going to, since we have no co-author today in the room, we suggest that we keep the discussions or the more important discussions for the end of the talk, for the last 15 minutes. The talk is recorded. And next week, we have Ben Golub from Northwestern University, who's going to talk about social learning in a dynamic environment. Meg, thank you for coming, and the screen is yours.
Okay, thank you very much, Angel. Thank you to all the organizers, and especially thank you to Peter and Nageeb for agreeing to be my panelists. Okay, so Angel has already given you the title. This is joint work with Eszter Kabos, who was a former student of mine in Oxford. Eszter is now fully occupied helping to run the city of Budapest, so unfortunately is not participating. So we're all familiar by now with the idea that when individuals learn, not only from private sources, but also by observing the choices of previous decision makers, information may fail to be aggregated, and consequently incorrect herds may result. And these models have been helpful in understanding choices over phone operating systems, restaurants, investments, technology adoption, diets, etc. The conventional wisdom concerning models of observational learning seems to be that relative to equilibrium outcomes, efficiency would be improved if individuals relied more on their private signals and less on the choices of others. But most analyses of observational learning focus on whether or not complete learning obtains asymptotically. We're interested here in developing a flexible framework for performing welfare analysis of equilibrium of decision rules in environments where learning is incomplete. We want to use such a framework to first of all, ask and answer the question, is the conventional wisdom correct in general? And to really identify under what circumstances and for what reasons informational externalities arise. So we have three contributions in this paper. First is to develop a model in which we can analyze steady states of environments with observational learning. We work with the most familiar, we start with the most familiar observational learning setting, one in which there's a binary state, every individual chooses one of two actions and signals are continuously distributed. Each agent observes with noise a finite set of predecessors' choices. And in steady state, each agent will be using the same decision rule to map their private signal and their observations into their choice. We will characterize equilibrium steady states as fixed points, and then we can formulate the planner's objective in such a steady state environment very simply. The planner's welfare objective is simply the expected payoff of an agent in the steady state. We can then move on to perform a welfare analysis of stationary decision rules, where the planner, in designing the rules, can use no more information than the agents use in equilibrium. Our second contribution is to use this framework to show that the conventional wisdom is at best incomplete. So first of all, we show that whether there exist welfare improving adjustments to decision rules and what form they take depends on the observation structure. We show in what we call our benchmark model that there is in fact no scope for the planner to improve welfare in a symmetric environment where each agent observes with noise the choice of only one predecessor. And we then show that for some observed data, welfare may be raised by having agents place less rather than more weight on private information. Our third contribution is to show that by working with more general observation structures, we can identify two distinct informational externalities, determining the existence and the form of welfare improving adjustments to decision rules. So let me say a little bit about these two distinct informational externalities. We call them the dispersion effect and the mean effect. By the dispersion effect, we refer to the fact that agents do not internalize the value of spreading their followers' posteriors. Now, this externality is also present in the canonical whole history observed setting, but as you'll see in our model, its implications for the form of welfare improving adjustments are richer. The second information externality that we identify, we call the mean effect. And by this, we mean the fact that individual optimization may not coincide with maximization of followers' mean or expected degree of confidence in the state that's indicated by the data. And this externality is absent in the canonical whole history observed setting. So here's an outline of what I want to do today. I'll begin by talking about related literature. I'll then present the model and the key definitions of steady state and equilibrium steady state. I'll then turn to our benchmark analysis, in which we demonstrate that the equilibrium steady state is in fact welfare optimal in a symmetric environment where each agent observes with noise the choice of only a single predecessor. I'll then introduce the two types of informational externalities that emerge with more general observation structures, and I'll illustrate them by presenting versions of the model where each of them operates in the absence of the other. And then if I have time, I'll conclude by talking briefly about a version where both of the externalities are present.
Meg,
yeah,
I have a question. Just to piece together the motivation, is the development, do you see the development of the framework as being something that's necessary to ask the motivating question, or would you say that the motivation for this new framework is to see the mean effect?
So that's a very good question. I think that the framework the framework certainly facilitates identifying the mean effect. You could identify the mean effect in versions of the model that were not steady state, but you can identify it much more clearly by giving yourself the flexibility to vary the observation structures quite a lot, which is made easier by the steady state analysis. Okay, so let me talk briefly about related literature. Of course, there's a huge amount of related literature, and apologies to many of you whose papers I won't have time to mention. I want to mention two categories, two classes of papers, which are particularly related. The first class is papers that analyze welfare improving adjustments to decision rules in settings where agents observe the whole history when it's their turn to act. So importantly, Peter Sorensen, Lona Smith, and Tian have a paper forthcoming in the Review of Economic Studies where they analyze the planner's solution to the canonical whole history observed model. And they show that the conventional wisdom holds. The planner would like agents to weight their private information more. There's a paper in the computer science literature by Perez et al., which performs an asymptotic analysis of the planner's optimal frequency of forcing the agents to rely only on their private signals. So they restrict the planner to intervening in a very specific way, and they analyze what's the optimal way for the planner to do that. There's an old paper of my own called Learning from Course Information, which is very relevant here because in the optimal the decision maker in that paper, their optimal dynamic strategy for biasing course observations turns out to yield insights for the planner's problem here. But what I want to stress is that in all of the papers I've mentioned, the only informational externality is the dispersion effect. And furthermore, there's no steady state analysis. That last remark brings me to the second category of related literature, which is steady state analyses, where each agent has a bounded observation window. And I mentioned two, Raphael Levy, Pesky, and Vier, and I know that two of those three at least are present today, and also a paper by Dasarata, Golub, and Hack. The second paper is the one that's going to be presented here next week. These are both analyses of equilibrium steady states in an environment where the state of the world evolves. The focus of these papers is different from ours. The paper by Levy et al. Studies the impact of endogenous private information acquisition, and Dasarata et al. Study the impact on observational learning of network structure. Neither paper focuses on performing a welfare analysis of how a planner would wish to adjust agents' decision rules.
Meg, can I ask a question here?
Of course.
So in relation to your key motivation and this literature review, you would say the mean effect is simply not detectable in the models with an expanding history, and does it then have to do with the sort of scarcity of the history in a way?
I will give the precise argument later, Peter. And I'm worried now that if I give the answer, the language I'm appealing to may not be completely clear. But I promise you that when I launch into discussing the mean effect, I will articulate clearly why in your environment it doesn't arise.
Okay.
So thank you for raising that, and of course come back to me if you're not happy with what I ultimately say. Okay, good. So let me present the model, and I'll begin with the signal structure. There's a binary state of the world, which it takes the value low or high, L or H, which is unchanged over time. As you'll see in a few slides, I'm going to be introducing recording error, which will be analogous to an evolving state, but it's, for my purposes, simpler to work with an unchanged state of the world. There's a symmetric prior shared by all agents over this state of the world, so low and high are equally likely. Each agent, before acting, observes a private signal, sigma I, which has support on the whose support is the open interval 0, 1. In state omega, sigma I has a probability density F sub omega. The private signals are IID across agents, conditional on the state. We assume strict monotone likelihood ratio property, so this likelihood ratio is strictly increasing in sigma. To be able to analyze first order and second order effects, it's convenient to assume that the likelihood ratio is continuous as well, and we'll assume that it approaches infinity as sigma goes to 1 and 0 as sigma goes to 0. Given the recording error that I'm going to shortly introduce, the equilibrium steady state cutoffs will, the recording error combined with this assumption will ensure that the equilibrium steady state cutoffs are always interior, and that's going to ensure that my welfare analysis is non-trivial. I don't want equilibrium cutoffs at the boundary where one type of adjustment is not possible. I'm going to assume throughout that the signal structure is symmetric with respect to the low and the high state. And by that, I mean that the conditional density conditional on the low state is the flipped about a half version of the conditional density conditional on the high state. Or in words, seeing a value of sigma less than a half is exactly as strong a signal in favor of the low state as is seeing the value 1 minus sigma is a signal in favor of the high state. So for example, to fix ideas, here's a simple example of two conditional densities that satisfy my symmetry assumption and that satisfy NLRP. Now, given the symmetry assumption that I've just made on the signal structure, there's a nice reinterpretation that I will frequently invoke. We can think about each agent's private information as consisting of an indicated state. So if sigma is less than 1/2, the indicated state is low. And if it's greater than 1/2, the indicated state is high. And the strength of signal, which is just 1/2 plus the magnitude of the distance of sigma from 1/2. I'm going to use P, which is always at least 1/2, to denote the strength of the signal towards the indicated state. So P is just sigma if sigma is bigger than 1/2, and it's 1 minus sigma if sigma is less than 1/2. And the symmetry of the signal structure with respect to the low state and the high state implies that the conditional distribution of P, the strength of the signal toward the indicated state, is the same, whether the state is low or high. Okay, so let me turn to the environment. I'm going to be analyzing a stationary environment, by which I mean the state omega, the signal structure, the number of agents acting, the strategy space, and the observation structure is unchanged across periods. Time is discrete because I want to analyze steady states. It's natural to think about time beginning at -infinity. Each agent, when it's their turn to move, makes a binary choice of action. And I'm going to denote the two possible actions by no and yes. Each agent is risk neutral and receives a payoff of 1 if they choose the action no when the state is low, or they choose the action yes when the state is high, and receives a payoff of 0 otherwise. Each agent moves once, but a finite number of agents may move per period. And each agent receives information about the recorded choices of a finite set of predecessors. So to mention some examples, each of which I will be analyzing later on, we may have a setting in which one agent moves per period, each of them observing the recorded choice of their immediate predecessor. Or we may have a situation where one agent moves per period, each observing the recorded choices in order of their two immediate predecessors. Or we may have a setting where M agents move per period, each one observing a binary aggregate of the M recorded choices from the previous period. Okay, so we now come to what I term recording error. And this is introduced in order to ensure that the state of the world is not fully learned. In particular, with probability 1 minus theta, where 1 minus theta is less than 1/2, but bigger than 0, an agent's action is misrecorded, meaning if they actually chose yes, then their action is recorded as no, or if they actually chose no, their action is recorded as yes. These recording errors are IID across agents and across periods and independent of the state in action. Once an action is recorded, correctly or not, the recorded version, which I'm always going to call the datum, remains unchanged. Every agent who observes a given predecessor's choice sees the same datum, and the probabilistic structure of recording error is common knowledge. So, of course, I could have modeled this. I could have relaxed some of these assumptions. This is the simplest, that, to my mind, way of introducing a friction that serves the purpose of ensuring that in the equilibrium steady state, we won't have complete learning, and hence we can perform a non-trivial welfare analysis. An alternative model in which the state follows a stationary Markov process, flipping with probability 1 minus theta after each period, is in fact isomorphic to our benchmark 1 datum setting.
Meg, just to clarify, without a recording error, the reason that you would have complete learning is because of the unbounded likelihood ratios?
Okay, so I didn't actually. Okay, essentially yes, but if I didn't have the unbounded likelihood ratio, I would have the equilibrium steady state being at the corner, being at the point where everybody relies only on the past data and not on their private signal. As a steady state model, that's not a very appealing model because it raises the Grossman-Stiglitz paradox. If everybody is relying only on the observations and not on their signal, how did the information get into the state? So it really is, to my mind, much more informative to have a model with recording error in which we're sure that the equilibrium cutoffs are away from the corner. And I think it tells you more. I'll try to remember to come back to your question, Nageeb, when I talk about the benchmark model. But thank you for raising it.
Great, thank you.
Okay, so in the environment that I've described, cutoff strategies are going to be optimal for the agents. In particular, if the state indicated by the private signal matches the state that's more likely given the observed data, then the agent will choose the action indicated by the private signal. And if the state indicated by the private signal is opposite to that indicated by the observed data, then there'll be a critical strength of the signal, call it P tilde, which varies with the observed data, such that the agent will follow the observed data if the private signal is sufficiently weak, and will follow the private signal if it's sufficiently strong. Now, my terminology is going to be the following. When the cutoff that's used, P tilde, decreases, so moves toward a half, the set of signal realizations that outweigh the observed data expands. And when P tilde decreases, we'll say that the agents are putting more weight on their private signal and less weight on the observed data. So P tilde moving towards a half means that the private signal will outweigh the data more frequently, and I'll refer to that as putting more weight on the private signal and correspondingly less weight on the observed data. The opposite change in P tilde increasing, corresponds to agents putting less weight on their private signal and more weight on the observed data. Okay, so we're now ready to define steady states and equilibrium steady states. Suppose that all agents across all periods use the same strategy as a function of the observed data. For each underlying state and each common cutoff strategy, which I'll just write as P tilde as a function of the data that is observed by the agents in period T will follow a Markov process. For a common cutoff strategy, P tilde of data, the steady state of the economy is described by the stationary distributions of the two Markov processes, one corresponding to each possible underlying state. And in an equilibrium steady state, each agent's optimal strategy, taking as given their conjecture about the common cutoff strategy used by all predecessors, will actually match the conjectured common cutoff strategy of all predecessors. So an equilibrium steady state is a fixed point. Having defined a steady state, we can now define the planner's welfare objective, and it is simply to maximize the probability in steady state that each agent chooses correctly. In other words, receives payoff 1 rather than 0. So what we're doing is we're assuming that the planner chooses a common stationary decision rule for all agents, which depends only on the data observed by each agent. So in particular, we're not allowing the planner to use more information than the agents themselves have. We will ask, is the equilibrium steady state welfare optimal? And if not, what changes in cutoffs locally generate improvements in welfare? Or in other words, in which direction, if any, would the planner want to nudge the agents? As you'll see, I will sometimes present global optimality results for the planner, but I'm really more interested in the local welfare, the possibility of local welfare improvements, and if there are some, which direction the planner would want to nudge the agents. The virtue of the steady state approach is that it transforms the planner's problem from a dynamic one to an effectively static one. That then makes the question that I'm posing easier to answer, and in turn allows me to consider a wider range of observation structures and thus identify more effects. Okay, so let's turn to what we call the benchmark. Suppose only one agent acts in each period, and each agent observes only the recorded datum from the previous period. I will say that a decision rule, whether for agents or for the planner, is symmetric if it uses the same cutoff level p tilde, in other words, the same critical strength of private signal, whether the observed datum is no or yes. And for this benchmark model, we have the following proposition. For any probability of recording error, there's a unique equilibrium steady state, and in it, agents use a symmetric strategy. And the equilibrium steady state decision rule is optimal for the planner among all stationary rules, whether symmetric or not. So I want to convince you of this result in two ways. First, by showing you a little bit of the mechanics of the model, and then by talking you through the economic logic. So in terms of the mechanics of the model, suppose all agents use a symmetric strategy with a cutoff p tilde. There are two crucial functions which determine the transition probabilities from one state to the next. So A of p tilde is defined to be the probability that the agent acting in period t sees a correct datum generated from the previous period, conditional on his predecessor having seen a correct datum, and conditional on his predecessor having used cutoff p tilde. A of p tilde is just a smooth version of the conditional CDF conditional on the low state, smoothed by the presence of the recording error. B of p tilde is the probability of the agent in period t seeing an incorrect datum, meaning a datum that doesn't match the state, conditional on his predecessor having seen an incorrect datum and having used cutoff p tilde. And that's just a smoothed version of the conditional CDF conditional on the high state. So in terms of pictures, A and B are just smooth versions of CDFs. The monotone likelihood ratio property tells us that A is everywhere above B. Unlike CDFs, these functions run from 1 minus theta to theta, but the other properties all follow from the MLRP. These two functions entirely determine the transition matrices for each underlying possible state. If the state is truly L, this is the transition matrix where the datum generated in the previous period describes the rows, and the datum generated in the current period is the columns. And because of the symmetric environment and the symmetric strategies, this right-hand matrix is just a permuted version of the left-hand matrix where the rows and columns labels are permuted. Now in steady state, seeing a datum of no is exactly as strong a signal in favor of the low state as seeing a datum yes is in favor of the high state, which says that these two likelihood ratios here are equal. And furthermore, just doing a simple computation of the stationary probabilities for these two Markov matrices, that common likelihood ratio, or in other words, the informativeness of the last period's datum in steady state, is just given by this ratio here, 1 minus B of p tilde over 1 minus A of p tilde, which is always bigger than 1. So that tells us the steady state informativeness of what each agent sees before they choose their action. Now, each agent is going to take the p tilde used by all their predecessors, and hence the steady state informativeness of each possible datum is given, and then optimize by choosing the symmetric strategy with a cutoff of p hat that equates this likelihood ratio to the likelihood ratio summarizing the informativeness of the observed datum. And given that B and A are just smoothed values of the CDFs, this likelihood ratio simplifies to B prime over A prime. In an equilibrium steady state, the optimal cutoff for each agent, taking as given the common conjectured cutoff for all previous agents, is just that common conjectured cutoff. It's a fixed point. Or graphically, the equilibrium steady state is value of P, P1 ESS, where these two curves intersect, the informativeness of the datum in steady state and the likelihood ratio for the critical value of the signal. And what I want you to notice from this picture is that the steady state informativeness of the datum is in fact maximal at the equilibrium steady state. The intersection occurs at the point where this curve is maximized. So now I want to talk you through what this is telling us and talk you through the bit of the proposition that this isn't telling us. So what the analysis that I've just talked you through does tell us, and I want to reinterpret it, is that the equilibrium steady state is welfare optimal among all symmetric stationary decision rules for the planner. Let's explain that in different words. With symmetric rules, each agent's degree of confidence given the observed datum is the same whether the datum is no or yes. Therefore, for the planner, maximizing the steady state probability that each agent chooses correctly is equivalent to maximizing each agent's degree of confidence in the datum that they see. Now, each agent's privately optimal cutoff maximizes their own probability of making a correct decision, or equivalently, it maximizes the probability that the history observed by the next agent, which is the currently generated datum, is correct. Hence, there's no gain to the planner from distorting the agent's symmetric cutoff rule away from the equilibrium steady state level. But that's not all the proposition tells us. There's a second part to the proposition. We need to understand why the equilibrium steady state is welfare optimal, even when we allow the planner to use asymmetric decision rules. So starting from the equilibrium steady state, in which, as we know, the agents use symmetric decision rules, suppose the planner considers introducing a small asymmetry in the agent's common strategy. For example, suppose that the planner has the agents makes the agents slightly less likely to choose no after observing a no datum, and slightly more likely to choose yes after a yes datum. Okay, so this would be an asymmetric strategy. This change in the agent's decision rule would raise the follower's degree of confidence, would raise, in fact, all agents' degree of confidence after seeing a no datum, but would lower it after a yes datum. So if the planner tells agents to bias their rule slightly against no and slightly in favor of yes relative to the equilibrium, that's going to mean that agents become more confident when they see no and less confident when they see yes. But since starting from the equilibrium steady state, agents' degree of confidence is the same, whether the datum is no or yes, this spreading of agents' posteriors has no first order effect on welfare. Furthermore, since the planner is choosing a stationary decision rule for the agents, and therefore is adjusting all agents' strategies at the same time, the agents are not able to adapt to their new posteriors. And in fact, the agents are forced to adjust their cutoffs in the wrong direction. And because they're forced to adjust their cutoffs in the wrong direction, this asymmetry has a negative second order effect as well. So consequently, any asymmetries in the decision rule will lower steady state welfare. we can in fact generalize the conclusion from this benchmark model to consider stochastic sampling of a single datum. So here's the following corollary. For any number of agents choosing per period, not necessarily one, and any stationary stochastic sampling rule that samples one agent's datum from some previous period, the unique ESS is the same as in the model with one agent per period and a one period window. And the equilibrium steady state decision rule is optimal for the planner among all stationary rules. So our welfare optimality of the equilibrium steady state generalizes as long as we stick to agents observing, generalizes to stochastic sampling as long as we stick to agents observing a single datum. Okay, so I'm now ready to turn to identifying the different types of externalities that can arise and in which environments. And as I said, we call the two types of externalities the dispersion effect and the mean effect. I'm going to present them one at a time to make their logic clearest. By the dispersion effect, I mean the fact that agents do not internalize the value of spreading their followers' posteriors. When the posterior degree of confidence that an agent holds in the state indicated by the data varies with the realized data, then variability of posteriors is beneficial, other things equal, because agents can adapt to their posteriors and so their payoff function is convex. When I say other things equal, I mean holding fixed the expected posterior degree of confidence in the state indicated by the data. And what I've been emphasizing in the benchmark model, with only one datum observed in symmetric decision rules, this effect is not going to arise because followers' posterior degree of confidence in the datum is exactly the same, whether they saw no or yes. So no spreading of posteriors is possible. Schematically, imagine the posterior here and suppose that according to what data you see, your posterior may be down here at this low black dot or up here at this higher black dot. A change in your predecessor's decision rules that spreads your posteriors, lowers your low posterior to this purple dot, raises your high posterior to this purple dot, will be beneficial for welfare, even if you can't adapt optimally to it, as long as we started from a situation in which you are adapting optimally to your posteriors. So let me illustrate the dispersion effect in what seems to me the simplest version, simplest modification of our benchmark model. Suppose now that one agent acts each period, and the agent in period T observes the ordered data generated by the two immediate predecessors. And I'll call this datum from T-2 and datum from T-1. I'm going to focus on symmetric strategies, and I now will need two, the cutoff will be, the strategy will be described by two numbers, S tilde and D tilde. S tilde will be the cutoff used when the observed data match, S for same. So when the observed data are either no, no, or yes, yes. And D tilde will be the cutoff when the observed data do not match, when they're different. And I'm sorry about D having two roles. So D tilde will be the cutoff when the observed data are either no, yes, or yes, no. For D tilde, I need a sign convention. I will use the convention that if D tilde is bigger than a half, that means that the agent chooses the action that matches the earlier of the two data points, unless their private signal is sufficiently strong in favor of the opposite action. And what I want to emphasize here is that in steady state, no matter what cutoffs your predecessors have been using, non-matching data leave beliefs unchanged from the prior, while of course seeing matching data means you're more confident than the prior. So therefore, agents' posteriors really are variable here according to whether they see matching or non-matching data. And therefore, the cutoffs S tilde and D tilde can affect the dispersion of these two unequal posteriors. So for this model, we have the following proposition. We have one agent per period, each observing the ordered data from the two previous periods, and symmetric decision rules. There exists a unique ESS, and in it, the cutoff that agents use after seeing matching data is strictly tougher than the cutoff they use after seeing non-matching data, which is exactly a half. So when agents see non-matching data, they fully rely on their private signal. They rely on their private signal for sure. Whereas when they see matching data, there are some realizations of their signal that are outweighed by the matching data. And the welfare result, the planner can increase welfare by raising the cutoff following matching data from a half, or lowering the cutoff raising the cutoff following non-matching data from its equilibrium value of a half, or lowering the cutoff following matching data from its equilibrium value. So this picture actually shows slightly more than the proposition says. We've got the cutoff following non-matching data on the horizontal, the cutoff following matching data on the vertical. This is the equilibrium in the benchmark model, and this is the equilibrium steady state in the model with observing two ordered data points. And what the picture shows you is that the planner's optimum lies in the interior of this region here. The proposition says that the planner can raise welfare by either raising D from this equilibrium steady state or by lowering S. So firstly, I want to explain why this result is an illustration of the dispersion effect, and then interpret it in terms of what it tells us about how welfare can be, what adjustments to how much agents weight their private information improve welfare. So from the equilibrium steady state levels, as we saw in the proposition, welfare can be improved by raising the cutoff following non-matching data from a half and lowering the cutoff following matching data. Both of these changes spread followers' posteriors because both of these changes reduce the probability that the next agent will see matching data. So therefore, both increase the follower's degree of confidence after they see matching data. At the same time, though, both of these changes leave non-matching data neutral. They leave the posterior following non-matching data exactly at the prior. So the higher posterior has gone up, the lower posterior has stayed the same. So that's an increase in the dispersion of the posteriors. Increasing D tilde from the equilibrium steady state level makes each agent put more weight on the observed history and less weight on the private signal. Because at the ESS, agents are relying entirely on the private signal when the data do not match. And since I've just shown that the planner can gain by moving D tilde away from a half, that means that the planner can gain by having agents put some weight on the observed history and therefore less weight on the observed signal. So the welfare improving adjustment to the cutoff following non-matching data is opposite to the conventional wisdom. On the other hand, the welfare improving adjustment to the cutoff following matching data is in fact in line with the conventional wisdom.
Meg, is there a simple...
Nageeb, go ahead.
Oh, I was going to ask, is there a simple intuition as to why agents rely entirely on their private signal when data do not match?
Yes. We're in a steady state, Nageeb. So every data point is equally informative. So if you see one no and one yes, they cancel each other out.
But I guess that the person, suppose I saw a yes and a no, I know that the person who saw the no saw the yes right before and chose to go no. So there is that asymmetry.
It's still the case that the two cancel out. And that's why and in fact, they cancel out, as I said a couple of slides ago, whatever the predecessors are using. I see where you're coming from, but the simple intuition is what I said.
Okay.
And this is just a stark illustration of it's very easy to see why the agents are weighting more here, are weighting their private signal less and the observed history more. Peter.
Still, there was your sign convention. I mean, it seems a bit arbitrary to say.
Oh, but my sign convention. But my sign
is relying more on the private signal or less. I mean, it kind of depends on what signal you get.
I don't think my sign convention is really driving anything here. I mean, if I'd signed it the other way, then I would have just said that the optimal way to adjust D was to move it down. But I still think that this, maybe you're asking me, why is this really putting less weight on the private signal? But it seems to me that the maximal weight on the private signal is when you do exactly what the private signal says. There's no range of P that leads you to overrule what the private signal says. So any D that's not equal to a half is putting some weight on history and is allowing something about the history to dictate the action rather than D equals a half, which is allowing the private signal entirely to dictate the action.
But you're not really in a direction, you're not really going more with your signal and against the history, because the history was neutral in a way, didn't really indicate what to do.
I could have given you, let me give you another example right now.
Thank you.
The same qualitative result arises with a one period window and an asymmetric prior. Okay, so now let's suppose that the prior probability of the high state is less than that of the low state. Okay. Now at the ESS, an agent is less confident after seeing a yes datum than after seeing a no datum. Okay. So the ESS cutoffs using the obvious notation are going to involve a smaller critical value of P when you see a yes than when you see no. Okay. The planner can increase steady state welfare by raising the cutoff following yes and lowering the cutoff following no from the ESS. And as long as this cutoff here is bigger than a half, raising it, I hope you will agree, leads to agents weighting their private signal less, and similarly lowering end leads to agent weighting their private signal more. So this doesn't involve the half semantic issue we just debated. And I hope you will agree an increase in Y it corresponds to the agent weighting their private signal less.
Agree. This is in a way a better example. But,
okay. Okay. Thank you.
Then you have the two things. But okay, we can debate it later.
Okay, but thank you. That's helpful. Okay, so let me turn now to the canonical observational learning model in which the agents observe the whole history of choices. So Peter's recent paper studies the problem of a planner in this environment who is choosing agents' cutoffs to maximize the discounted sum of agents' expected payoffs. And I want to argue that in Peter's model, with the whole history observed, the only externality is the agent's failure to internalize the value of spreading their followers' posteriors. Peter's paper provides a regularity condition on the signal structure, which implies that welfare is increased by having agents put more weight on their private signal, move their cutoffs towards a half, for all histories. In contrast, our steady state analysis here shows that welfare improving adjustments may lower or raise the weight on the private signal, depending on the realized data. I now want to talk about the mean effect, and I'm going to get to Peter's question about why it doesn't arise in the canonical whole history observed. But let me remind you of what I mean by the mean effect. I mean that individual optimization may not coincide with maximization of followers' expected degree of confidence in the state indicated by the data. Whether these goals coincide, and if not, the consequences for welfare improving adjustments will depend on the amount of data available to the followers and on how the data are aggregated. We saw in the benchmark analysis that when only a single agent's datum is observed, these goals do coincide. This externality, this mean effect, is absent in the canonical whole history observed setting. And the argument is the following. When the follower is going to see all the data that you see, plus your own generated datum and nothing more, in equilibrium, your generated datum is going to become the decision indicated by the data for the follower. So when you maximize your own probability of choosing correctly, that maximization coincides with maximizing the follower's expected degree of confidence in the state indicated by the data. The mean effect arises whenever an agent's generated datum will not necessarily become the decision indicated by the data for followers. And so what I want to do is illustrate the pure mean effect in what seems to me the simplest way. I want to suppose that M agents act each period, and for the mean effect to arise, M has to be at least 3. Each agent observes only a common, potentially noisy binary aggregate of the data generated in the previous period. So I'm going to model a noisy aggregation process in a general way. If K out of M data points in a given period are no, I'm going to let gamma K represent the probability that agents in the next period perceive the aggregate as being no. It's natural to assume gamma K is non-decreasing, and to keep the environment, the observation environment, symmetric, I'm going to assume the aggregation process is symmetric with respect to no and yes, which corresponds to this condition. Given a symmetric aggregation process and given agents use symmetric rules, each agent's degree of confidence in the observed aggregate is the same whether the aggregate takes the value no or yes. So in this setting, there's no role for spreading followers posteriors, just as there was no role in the benchmark model. So this setting is going to allow me to demonstrate the pure posterior mean effect. And to save...
Sorry, just to understand this, would it suffice if I just imagine that I observed what the majority of people chose with some noise, with some recording error?
So that's one version of the model, Nageeb. That's how I started. That gives you one result. I want to model the aggregation process flexibly because I want to show you what properties drive the result in one direction or the other.
Excellent.
To save notation, let me assume M is odd, but the result carries through as long as M is at least 3. And I'm going to contrast 2 different types of aggregation process. Okay. The first one I'll call a process that displays sensitivity to changes diminishing toward the extremes. And the second one, sensitivity to changes rising towards the extremes. So on the left-hand side here is Nageeb's suggestion. I've drawn it for 3 agents, and the aggregation process is just noiseless majority aggregation. This is an example of process of form 1. The aggregation, the probabilities gamma begin convex and then they turn concave. The second type of aggregation process is exactly the opposite. They begin concave and then they turn convex. So this process on the right, the aggregate tells you nothing. The aggregate is perfectly noisy if the 3 people in the previous cohort split 2-1 in either direction, but it's noiseless if they all chose the same, if they all generated the same datum. Okay, and denote the cutoff P tilde in a symmetric ESS strategy by P sub gamma ESS, because it depends on the aggregation process. And the result is as follows. If the aggregation process displays sensitivity to changes that diminishes toward the extremes, then the planner can increase welfare by lowering the cutoff from the equilibrium value. And if the aggregation process displays sensitivity to changes that rises towards the extreme, then the planner can increase welfare by raising the cutoff from the equilibrium value. So the optimal welfare improving adjustment can go either way, depending on what type of aggregation process we have. To help you see this result, which I will go into in detail in the next couple of slides, it's helpful to think about the intermediate case where gamma k is linear in k, so aggregation is equally sensitive to all changes in data. And furthermore, gamma k just runs from 0 to 1. So gamma k equal to k over m says that the probability that the aggregate is no is exactly the fraction of no's generated by the previous cohort. But that's exactly equivalent to random sampling of one datum from the previous cohort. And we already know from the corollary in the benchmark model that with random sampling of one datum, the ESS is welfare optimal. So this linear, yep.
Oh, yes, just to remind you, 5 minutes remaining.
Yes, thank you. So this linear aggregation process is one in which the ESS is welfare optimal, and depending on which side of it we're on, we're going to get the welfare improving adjustment being either to lower or raise the cutoff. Okay, so let's interpret this. At the equilibrium steady state, the derivative of welfare with respect to the cutoff has the sign of the derivative with respect to the cutoff of the probability that the aggregate is correct, okay? However, the probability that the aggregate is correct is not what each agent is maximizing, okay? The probability that the aggregate is correct would be maximized if each agent conditioned on realization of the others' data, the data of others in their cohort, such that their own datum will change the aggregate. In the example at the left, which is what Nageeb proposed, noiseless majority aggregation, clearly conditioning in this way would mean conditioning on others, the two others in your cohort, one of them generating no and one of them generating yes. Now, if you conditioned in addition to if you conditioned on this event, as well as on the aggregate that you saw, this would leave you less confident that the state matches the observed aggregate, since at the equilibrium steady state, agent strategies are biased toward the aggregate. So therefore, conditioning in this way would lead you to use a lower cutoff, and hence welfare would be raised by agents lowering their cutoff from the equilibrium steady state value, thus weighting private signal more. On the other hand, let's do the same logic for this case. This case is only the extremes are informative. Only the extremes are distinguishable. In the example here, the appropriate conditioning would mean conditioning on the others choosing matching actions, both no, no, or both yes, yes. And because conditioning on this event means conditioning on the complement of the event from the previous slide, conditioning in this way would increase the agent's confidence that the state matched the observed aggregate. And therefore, welfare would be raised by agents raising their cutoff from the equilibrium steady state level, which corresponds here to weighting, agents weighting their private signal less and the observed history more. Okay, I want to just mention a couple of, in my last 2 minutes, I want to say a couple more things about the mean effect. Firstly, though I've illustrated the mean effect in a setting where data is aggregated, this effect can arise even without aggregation of data. In this case, when it arises in a setting even without aggregation of data, we're going to have the dispersion effect arising as well, since the degree of confidence will be variable. The key point is that the mean effect arises whenever an individual's generated datum won't necessarily become the decision indicated by the data for followers. Or in other words, whenever an individual's datum is not certain to be pivotal for what state their followers believe more likely. And if I had more time, I would illustrate a setting where both of the effects operate, in fact, operate in the same direction, by talking you through a setting where each agent sees the data generated by their three immediate predecessors. But I don't have the time, and so I think I will just conclude. I hope I've convinced you, or at least left you willing to entertain the idea that a steady state analysis of observational learning is a very flexible and insightful approach for welfare evaluation of equilibrium decision rules. We've shown that whether there exist welfare improving adjustments to decision rules and what form they take depends on the observation structure. We showed that equilibrium steady state decision rule is welfare optimal in a symmetric environment where agents observe only a single predecessor's datum. And we've identified two distinct informational externalities, the dispersion effect and the mean effect, and have shown that both types of externality can, for some observed data or for some data structures, make it optimal for agents to place less rather than more weight on their private information. Thank you.
Thank you very much, Meg, for this insightful talk. So we're going to move next to the section of questions, and
Super.
I'm going to start with the panelists. So let's start with Peter first. And Peter, do you want to start with your questions, maybe?
Yes, thank you very much, Meg. It was a very insightful presentation indeed, and a very nice model, I think. So I'm still wondering about this kind of scarcity of memory here, maybe. That some of your examples in particular were turning on the case where you would see only one predecessor. But I guess in the herding model intuition, maybe the problem is that all of my predecessors tend to do the same thing too much. And then I look at that and it's not sufficiently variable. And I don't sufficiently get information about what they were thinking. And so perhaps you don't really capture that in a single observation model. And there's something else going on about this scarcity, really. You cannot afford to experiment too much with that one thing they see or few observations.
So if I think, Peter, about why my result that shows that the direction of welfare improving adjustments can be in either direction compared to your result, which shows that under your regularity condition, it's always in one direction. My explanation would be the following, and I do realize that I may not be understanding your way of thinking about things, but I would say in your model, firstly, as I tried to emphasize, the decision that each agent takes becomes the decision indicated by the data for their followers, okay? And in your model, the key, I should say, I know your model does not restrict to binary actions, but let's, for the purpose of this, just restrict to binary actions. The key issue for your model is how are the posteriors ordered? I'm making my decision today, and based on what I've seen, I think the low state is more likely. My predecessor just chose no, and that's the decision indicated by the data. I'm going to choose, when I choose my equilibrium cutoff level, how are the posteriors for my follower ordered according to whether I choose no or yes? And your posterior monotonicity ensures that if I choose no, he's going to be more confident than if I choose yes. And therefore, if I bias my decision today against no, I'm going to spread his posteriors. And that's going to apply whatever the history is. If we impose your regularity conditions, we know exactly how to spread my followers' posteriors, which is for me to bias my cutoff rule against the decision indicated by the data that I see. Now, in my model, at least for relatively simple examples, the steady state notion disciplines the ordering of the posteriors, which is why I don't need to impose any regularity conditions beyond MLRP. But the it's not the case necessarily that the action that I choose today will become the decision indicated by the data for the follower. So for example, the thing that I didn't get the time to show, suppose that in the version where each agent sees the data in order of their three predecessors, suppose the agent who's acting at time t sees no, no, yes, okay? The last guy chose yes, but because of the finite observation window, today's guy, the agent at t, doesn't think yes is the decision indicated by the data, okay? He thinks no is the decision indicated by the data. So, and that is going to result in, for this, I chose this example because the welfare improving adjustment in the cutoff relative to the ESS is to have the agent, in this case, bias in favor of no. So to weight the history more and the private signal less. So the property that you have in your model where the whole history is observed, that what the last guy did becomes the decision indicated by the data always, is crucially, and combined with your posterior monotonicity, tells you exactly how to spread the posteriors, and it's always by qualitatively the same adjustment, which won't be true here.
Okay, thank you.
Thank you.
I don't know the format. Can I ask something in a completely different direction, or should I allow Nageeb to do that?
So probably we can alternate with Nageeb, and later we can come back to you.
Yes.
Okay, I was going to say, Peter, you're welcome to go ahead. Okay, I'll just then ask a question, which is, so Meg, I think it's a great framework. I really like the framework a lot, and analysis that comes out of the framework, and in particular, the results that you get with these different kinds of aggregators. One thought that I had, so initially when you were presenting with the, I only observed the data from my predecessor. There was something about that argument that reminded me of the kinds of teams problem argument that Andrew McLennan had for beneficial information aggregation in a Condorcet jury theorem kind of setting, where the social planner and each individual decision maker in some ways have the same objective function. There's no way in which you'd want to, you know, what the individual is going to do in the voting problem is going to indeed be a socially efficient voting decision. And I think we sort of see this sort of wedge then also come up in the aggregator, which is part of the wedge that is coming up, is now it's no longer a team's problem. And so I was wondering whether there is indeed, whether this one could take this metaphor further within different parts of the paper.
That's an extremely intriguing question. I'm not familiar with the McLennan argument, but I will certainly go off and look at it. And I'm very interested in identifying analogies between the wedge, as you put it, that I identified and similar divergences in other contexts. And I have not explored voting models more generally in any detail, but your comment is the second one that makes me think that I ought to do that. I'll be keen to, you have more expertise than I do, so I'll be keen to get any further thoughts from you.
Excellent. Yeah. The second thing I was going to say was that I think so Mira Freak, Ryota Ijima, and my colleague Yuta Ishii have a paper on fragility of asymptotic learning that's recently in Econometrica. And they also have this kind of setting in which there's like a continuum of agents, and each individual can only observe the choice of their predecessor. And I remember the first time when the setting was described to me, perhaps because my inclinations are similar to Peter, I kept on trying to map their insights back to the standard observational learning model where you observe everyone's decisions in an expanding history sort of way. And I guess over time, I have just come to appreciate that maybe it's good for us to play around with multiple different observational and social learning models, because as they've done that mapping for me, I've seen it would be much harder to get their insights from a standard observational learning framework to some degree, that they would just have to do more work in different places. And that this helps isolate it.
So are they arguing that they would get qualitatively the same insights, but
you would get qualitatively the same insights, but the analysis certainly would not be anywhere near as clean or elegant or pretty. I mean, they have a beautiful picture in their paper that's similar to the beautiful pictures in your paper. And I think in the standard model, that picture, I don't know if they would be able to have such a nice picture.
Okay, thank you. That I will look more into that. I hadn't thought of their paper with that contrast in mind. Peter, I think did Peter want to say something?
Yeah, some of the literature you mentioned was looking at trying to improve learning by manipulating really the observational structure, allowing think about what people would see. You might think that really using your model here would be ideal for that, so you could experiment a bit with these things in your setting. Have you thought about going in that direction now?
I have, so I can use my aggregation model to say things that, at least as of now, strike me as fairly obvious about how changing the aggregation structure would change the equilibrium, would change welfare. More generally, I have thought about it, but have been trying to keep the focus relatively narrow. But I mean, tell me what particular questions, flesh out that suggestion a bit, and I'd be keen to hear.
Yeah, so for instance, when there were M people moving in the previous period, you could think about the optimal way of somehow aggregating it. I mean, you could even, just with your functional form gamma, you could think of the optimal way to do it.
Yeah.
That's a place to start.
Right. I think the optimal way is going to be noiseless majority aggregation. I can prove a monotonicity.
Nice. That's good.
Okay, good. Good. That's very helpful. I should say that, I mean, the other context, the other version of the question you asked that I have thought about is in comparing the one datum versus the two ordered data cases. And it's actually not I don't think it's in general clear that moving from seeing one datum to seeing two ordered data is necessarily beneficial. There are two opposing effects, the inefficiency versus the extra information. I can write you down examples where I know that the welfare is higher with the two, but I don't think it's true in general. So that's the other form of this that I've thought about.
Good. Thank you very much. So anybody from the audience wants to make a question? I mean, I have one that is basically a continuation of Peter's question. So, I mean, what I was wondering is whether the analysis of efficiency, marginal efficiency improvements that you do could be rephrased so to understand exactly as Peter was suggesting how to marginally modify the aggregation function. Because I mean, of course, I mean, I understand your answer to Peter, which is basically that I know what the optimal aggregation function is, but still, I mean, there may be constraints and there may be cost in moving towards full info. And then I mean, your insights about these marginal changes can also provide us insights about how to marginally change the aggregation function.
I agree with that. I have a result that says basically if you take any gamma k and to maintain the symmetry, the corresponding gamma m minus k, and you move it down a little bit, the gamma k down a little bit, the gamma m minus k up a little bit, that's going to improve the welfare. So in that sense, I do have a marginal result. I should say there are other questions that one might ask. For example, think about the 2-period window where we saw that welfare could be improved by lowering the cutoff following matching data and raising the cutoff following non-matching data. If the planner can do what I'm allowing him to do in my model, that's clearly going to be if the planner can achieve the adjustment in the way that I assume, just nudging the decision rules, that's going to be the best thing to do. But suppose that he can't. Suppose that he has information design available to him, but not nudges. It may be that he gains by garbling the information. This is not obvious. There's going to be a direct cost, and my analysis shows that there's going to be a benefit. So my conclusions are not going to be as strong, but I can argue if you did want to garble, if the planner did want to garble the information, I could tell you what direction he would want to garble it in.
Thank you very much. So we are at the end of the official time of the seminar. So I'm gonna stop the recording. I'm gonna declare the end of the seminar, but we can still hang around and have a more informal discussion with Meg Meyer. So please, feel free to stay, and thanks again for this insightful and excellent talk, Meyer.
Thank you for having me.
It was very nice to have you here.